Welcome back to our lecture number 7 about t-tests. We just discussed what a one sample t-test looks like, how to calculate a t-statistic, and went through some of these practices together. We're going to be coming back to some of these practices for the rest of this lecture as we talk about the other things that are important to report when we do hypothesis testing, starting with effect size. So let's talk about the different ways that we are going to report effect size. Excuse me, gotta get my notes up here. The different ways that we are going to report effect size when we're dealing with a t-test versus how we talked about it with the z-test. So d prime here, effect size, is called the estimated Cohen's d. And before we get into how to calculate this, let's do a brief recap of why it is important for us to report effect size when we are doing hypothesis testing. So hypothesis tests, remember, simply determine whether or not a treatment effect is greater than expected simply due to chance, which, especially when we do a t-test, is based solely on our estimated standard error. That is the only thing that helps us rule out chance. So it's possible for us for a very small treatment effect to be statistically significant, especially when you have a really large sample size. And in that way, it's important for us not just to report our p-values, but every time to report how big the effect size is, in addition to confidence intervals, which we'll talk about later today. So this d prime here, d with a little hat, is called estimated Cohen's d. And it's the same as the Cohen's d that we talked about before, but instead of using standard deviation in the denominator, we are going to use the sample standard deviation in the denominator. And as a result, the estimated Cohen's d is going to be an estimate of the size of the treatment effect in terms of the sample standard deviation. Another way that we can measure effect size, especially with a t-test, is by r squared. This is a slightly different way to measure effect size, and it also is going to have some different conventions. R squared is actually the measure of the proportion of variance in the outcome that is accounted for by the treatment. In other words, it's how much variance in our sample is due to treatment versus just normal variance between people. It's quantifying that number. And yes, right here, it's based on the idea that the treatment is the reason why the scores have increased or decreased relative to our population mean. The way that we calculate it is with this formula here, our t-value squared over our t-value squared plus our degrees of freedom. And what this really is showing us is we're putting the variability in our sample that is explained by the treatment and putting it in terms or comparing it to the total variability of our sample. These are just some size conventions here. When you have 0.01 for your R squared value, that's a small effect size. 0.09 is defined as medium, and then 0.25 or larger is defined as a large effect size. So we are going to go back to this study that we talked about in the first part of this lecture, where we talked about that study with infants, looking at attractive versus less attractive faces, where the researcher measured the amount of time that the infant was looking at each picture. Just as a reminder, the study used a sample of 9 infants, which will be important information for us. The data produced an average mean of 13 seconds for the attractive face, with the sum of squares of 72. So right here, this is going to help us kind of understand where R squared comes from and what it means when we're calculating R squared. So this distribution shows us that the null hypothesis said that the treatment, so the attractive, in this case, the treatment is the attractiveness of the faces, is going to have no effect on the infant's behavior. In other words, the null hypothesis said that the mean would be 10 seconds for each face right here. But we can see, because of this data in this figure, it's figure 9.5 from this textbook that we're using, the scores are not actually centered around the population, the hypothesized population mean. Instead, they're centered around the sample mean of 13. They're shifted a little bit to the right, right? Right. The shift from what we expected the center to be to what it actually is, that is our treatment effect, the shift to the right. And to measure the size of the treatment effect, we're going to calculate deviations from the mean and the sum of squared deviations in two different ways. So let's look into that a little bit. Here are two different figures that are going to show us a visual representation of what treatment effect is and variability based on treatment effect. So this top figure is showing us the original set of scores, right? The hypothesized, and for each score, I should say this, the deviation from the population mean, the hypothesized population of 10, mean of 10, is shown with a red line. So these are different sets of scores, right? And the deviation from the mean is shown with these red lines. So note that almost all of the scores in this original data set are located to the right of our population mean, our hypothesized population mean, excuse me. The shift to the right, like we said, is the treatment effect. We're seeing the treatment effect visually. Specifically, if we're putting it in terms of the experiment we're talking about, the shift to the right shows that the preference for the attractive face has caused the infants to spend more time, a higher degree of time, looking at the attractive photograph, which means that their scores are generally greater than 10. So thus, the treatment has pushed the scores away from the hypothesized mean of 10 and has increased the size of the deviations. Now, this bottom figure is what happens if the treatment effect is removed. In this situation, what we did to remove the treatment effect is we saw that the population hypothesized mean was 10. The sample mean was 13. That has a difference of 3, of plus 3. So we are just going to subtract 3 from every single one of the scores. And in that way, we are removing the treatment effect, essentially. So these are the adjusted scores. And once again, the deviations from the mean of 10 are shown in red lines. First, I want you to notice that the adjusted scores are now centered at the hypothesized mean of 10, indicating that there's no treatment effect, because that's our null hypothesis, right? That if there's no treatment effect, the mean of the sample is going to be the same as this hypothesized population mean. And also notice that these deviations, or these red lines, are noticeably smaller than they are when the treatment effect is in place. So in other words, the difference between, if we were to take the difference between this top graph and this bottom graph, we would be able to get the variability that is due entirely to the treatment effect. Essentially, this minus this gives us the treatment effect. But this is actually just a visual representation so we can understand what's going on. How are we going to get the numerical values that we need to plug in to our formula here? So this is how we're going to do that. To measure how much the variability is reduced when the treatment effect is removed, we're going to compute the sum of squared deviations for each set of scores. So in this left-hand table, we are seeing calculations for the original scores. And in this right-hand table, we're seeing calculations for the scores after the treatment effect is removed. So this left-hand side here represents this top, the original. Right-hand side represents when the treatment effect has been removed, or this bottom graph. So notice that, so this is going to represent the total variability, right? The total variability, we're going to say we take the score, we take the deviation from the mean, and then we square it, add it together, we get the total deviation. The total variability is 153. However, when we do the same calculations after our treatment effect is removed, this minus 3 here, we get 72. So what this 72 represents to me is the amount of variability that would be in the population regardless of a treatment effect. This is the variability that is unexplained. We don't know why it's there. There's no reason for it. It just exists. So if we take the total variability and we subtract whatever's unexplained, the variability that's unexplained, we're going to get the variability that is explained exclusively by the treatment effect. So total 153 minus unexplained 72 gives us 81, which is a score of the variability that is entirely explained because of the treatment effect, which I think is really cool. This value, actually, we're going to not just report it as a whole value. Usually you report this value as a proportion or percentage of the total variability, which is shown here. R squared is essentially just the variability explained over the total variability, 81 over 153. So in this case, it's going to be 0.5294, which means that 52.94% of the variance in the amount of time that the baby spent looking at the faces is accounted for by the level of attractiveness. Which is, anyways, this is a very, very cool way to report effect size. I highly recommend that you use this when you are reporting the variability of your treatment or of your t-tests. Okay, now let's move into when and how we're going to use confidence intervals. So the whole point of a t-test is we're using it because we have some unknown population values. We don't know what the mean is. So when we're reporting our values, if you remember from a lecture way, way back, we usually report statistical values based on the mean of a population, right? How much our values are above or below the mean of a population. But if we don't know the population mean, how are we going to report our findings? So up until this point, we've been talking about using a point estimate of the population mean, which is just when we take a single value as the best guess of our population parameter. And we've usually been using the mean of our random sample as our best point estimate for the population mean. Now we're going to introduce an idea called an interval estimate, which is when we determine a range of values within which we're pretty sure with a certain degree of confidence that the population mean falls within. We call this interval the confidence interval, which we've talked about before. The most common confidence associated with the confidence interval is 95%, and a typical confidence interval is symmetrical with the point estimate placed at the center. So let's look into how we are actually going to use this. So confidence interval as a review, this is something that we introduced in the last lecture, is a range of values that we are going to estimate from our sample statistics with a given probability that the range that we establish will contain the true value of the population parameter, usually the population mean. That's what it says here. An interval or range of values centered around a sample mean that is used to estimate an unknown population mean. And that, we talked in our last lecture about what a confidence interval is. We defined it, we introduced it. Now we're going to see how to actually use them and report them by using them to estimate this unknown population mean that we have when we have a t-test. We report it as such. This is the formula. We say that the unknown mean of our population is going to be our sample mean plus or minus our t-critical value times our estimated standard error. Cool. This is going to be kind of like a visual representation of what this confidence interval looks like. This is our t distribution, right? We're going to take all the possible t values from our sample and our population, right? And what we're going to do is we're going to use that two-tailed t critical values table, this one. Let's see if I can find it in a relatively quick way. This one right here. We're going to use this same table, but instead of using this proportion part to calculate our alpha, we are going to use it to say, for example, we want, right here, we're going to say, okay, we want the 80% of our t distribution to be in the middle, and we want 20% to be on the outside. So that's 10 and 10. We're going to essentially say we want a two-tailed 20% alpha value, essentially, even though that's not what this is. And we're going to use that to find our t critical values here. So here what we're saying is 80% of our total, and this is obviously with your degrees of freedom of 8. 80% of our t distribution values are going to be less than 1.397 and more than negative 1.397. 80% of our values are going to be within that area. 20% are going to be outside of it. And because 80% of all the possible t values are located within this middle region, we can be 80% confident that our sample mean is going to correspond to a t value in this interval. So that's what it's going to look like, but let's talk about how to construct it. So the first step we're going to do is we're going to select a sample size for our study, which is usually going to be based on either economic considerations, how much grant funding you have, how much resources you have for your study, or maybe like a power analysis, which we've talked about before. Then we're going to select our level of confidence. Usually you're going to go with a confidence interval of 95% or 99%. Then you're going to do your experiment. You're going to select your sample randomly. You're going to collect your data. You're going to calculate your sample mean, your sample standard error, all that kind of stuff. And then you're going to use all of that information to calculate the limits of your interval by looking up the corresponding critical t values in the t distribution table. So that's what these things are. You're going to look up these limits using your t-crit table. And then you're going to take all of that data and you're going to find the upper and lower limits of your confidence interval. The lower limit is going to be your mean minus your t critical times your standard error. And your upper is going to be your mean plus your t critical times your standard error. Let's look at an example. So if we go all the way back to if we go all the way back to that infants and attractive faces study, let's say we still have a sample size of 9, but let's say this time we wanted a 95% confidence interval. That's the second step, right? We're going to select a 95% confidence interval. We do our study, we figure everything out. We get a sample mean of 13. We get a sample standard deviation of 3. We calculate that our sample standard error is 1. After we've done all of those steps, you're going to use your t critical table. You're going to say, okay, my degrees of freedom is 8, right? 9 minus 1. And the value that I'm looking for, since we want 95% confidence interval, that means we want 95% of the t distribution to be in the middle, which means we want a 5% two-tailed distribution, essentially. You find that value, it's going to be plus or minus 2.306. We use all of that information to find the upper and lower limits of our confidence interval. So the lower is going to be your mean minus this value. So 13 minus your t critical times your standard error. And then your upper limit is going to be your mean plus that. So these are our limits here. So how we would report it is we would say, for this study, we have a 95% confidence interval of 10.69 to 15.31. So what that means in words is we are 95% confident that the population mean for the amount of time that infants spend looking at more attractive faces falls within an interval of 10.69 to 15.31. And remember from our last lecture, we said that if the interval does not contain 0, we can conclude that the effect of your treatment effect is significant. So since our interval does not contain 0, we can conclude that the effect of attractiveness is significant in the amount of time that babies spend looking at these pictures. Just a quick review. Remember that the width of our confidence interval, how wide it is going to provide information about how precise our estimate is. If you have a wider interval, it means that you have low precision in your estimate. If you have a narrow interval, it means you have pretty high precision. And the width of your confidence interval, how precise it is going to be affected by 3 things. Number 1, your sample size. If you have a larger sample size, you're going to have a narrower confidence interval because you have a larger set of data with which to make your estimate. Your estimate's going to be better when you have more data to make it with. Excuse me. The second thing that's going to affect your confidence interval is the standard deviation of the sample. If you have a larger standard deviation, you're going to have a wider confidence interval because your estimate's not going to be as precise. And then the amount of confidence. If you have a larger percentage of confidence, you're going to have a wider confidence interval, just because it's as your confidence gets higher, your precision is going to get slightly lower. This is just a really quick example of what happens when you increase your sample size. We're using all of the exact same data, except we're using a different sample size. And because sample size directly affects your degrees of freedom, it's also going to change your t-critical value. So these are the only two things we changed. Really, the only thing we changed was sample size, but that also ends up changing your critical zone. And that significantly narrowed our confidence interval. It went from 10.69 to 15.31 to 12.41 to 13.59. That's a much narrower interval, which means is just an example of how increasing your sample size is going to also give you a narrower confidence interval. And with that, we are done with our presentation here, and I'm going to leave that with you. And then in our next lecture, we're going to look at using a t-test again, but now using it for two independent samples, not just one. So I will see you in our next recording.